Is Amy Veprauskas, and she is a research associate in the Department of Mathematics at the University of Louisiana at Lafayette. She received her PhD in applied mathematics at the University of Arizona in 2016. Her research interests are in the field of mathematical biology. Her current work is focused on developing mathematical methods that can be used to examine the impact that disturbances such as oil spills may have on population processes.
All right, so I'm a member of the research group LATSI-GEM, which stands for Littoral Acoustic Demonstration Center Gulf Ecological Monitoring and Modeling. So our group consists of individuals from a number of universities as well as industry technology. And in terms of academic departments, we have researchers from a number of sciences, including marine science and physics, as well as engineering and mathematics. So as Chris mentioned, I'm actually a mathematician. All right, so the overall goal of our group is to gain a better understanding of how the Deepwater Horizon oil spill impacted marine mammals. In particular, our focus is on deep diving cetaceans, specifically sperm whales and beaked whales. And we have two approaches that we use to address this issue. So the first is using passive acoustic data collection. So we collect passive acoustic data, and from this data we identify echolocation clicks made by beaked whales and sperm whales. And from these click counts we can obtain estimates for regional abundances, both prior to and after the oil spill. So this information can tell us about the short-term impact that the oil spill had on these marine mammals. And then the second approach is developing some mathematical methods that can be used to better understand the long-term impact that the 2010 spill or other similar disturbances may have. So I'm going to start off by talking about the acoustic study. So we have three experimental sites, which we refer to as the northern, southern, and western site. Ooh. That didn't work. Okay. So you can see sorry, it's kind of hard to see, but the pink thumbtacks denote where our experimental sites were in 2010. So these sites are 9, 25, and 50 miles away from the oil spill, which is indicated by that little flame there. The map on the right, the green region shows where oil was known to be present in June 14th, 2010. So that's approximately 2 months after the spill occurred. And we can see that both our northern and southern study site were both within this region. So we chose these three study sites based on previous observations. Specifically, beaked whales were known to be abundant at the northern and southern site, and sperm whales at the western site. And then additionally, I want to note that one major difference between these sites are the water depth. So the northern and southern site, the water is approximately 1,500 meters, while the western site is more shallow at about 1,000 meters. So we're fortunate in that we have acoustic data from prior to the 2010 spill. So we have 2 weeks of acoustic data that was collected in July 2017 at both the northern and southern site. So this data we can use as kind of a baseline to understand what whale population abundances were prior to the spill. Following the spill in September 2010, we collected an additional 2 weeks of data at both the northern and southern site, and that's when we added in the western site. And then in 2015, from June to October, we collected 4 months of acoustic data at all three study sites. And more recently, from September 2016 to January 2017, we collected an additional 5 months of data. So this most recent data I won't be discussing in this talk because we're still processing it. All right, so to collect our data, we use what are called environmental acoustic recording systems, or EARS buoys. So on the left is a schematic of what these buoys look like. So they're anchored to the sea floor and they continuously collect data. So we deploy them, and this is a picture of a buoy pre-deployment. Then we later come back and we collect the buoys and we can process the data contained on them. So all of the data I'll be discussing today were collected using these ERAS buoys. I'll just say at each study site in every year, we have between 1 and 3 buoys, we have data for between 1 and 3 buoys, depending on how many were deployed and if they worked correctly. I want to briefly mention that we're also exploring collecting data using other mechanisms, including autonomous surface vehicles, as well as sea gliders, which are shown on the right there. All right, so once we've collected this data, we then have to go through and process it. So basically, we can use an algorithm that can detect clicks made by sperm whales and beaked whales. And in particular, for beaked whales, it can distinguish between clicks made by different species. So in the Gulf, we identified, at our study sites, we identified 3 species of beaked whale. They're the Cuvier, the Gervais, and what's been called the beaked whales of the Gulf, or BWG. So this last group has been recorded acoustically, but has never been visually observed. And this graph here is just a demonstration of how differences in the signatures of these clicks can be used to help identify which species is making the click. So the first row gives the frequency, and the second row gives the duration for these 3 species. All right, so once we've processed the data, we can create a graph like the following. So I apologize that that's a bit difficult to read. But what I have in the top row is the average number of clicks in every minute per day at the northern site for 2015. And this is combined for all 3 beaked whale species. And here the colors of the bars are being used to distinguish between the different months of the year that the data was collected. And then in the bottom row, we have the clicks made by each type of species. So in particular, when we look at this, we note that most of the clicks are being made by the Cuvier beaked whale, so that's that middle graph. A few are being made by the Gervais, and then there's very few from the BWG. We can make a graph for the southern site, and we see a similar pattern to this one. Meanwhile, if we look at the western site, we notice some differences. First off, there's less activity overall. And then we also notice that the Gervais, so that's that bottom right graph, are the most active in this region. And again, as with the previous one, we only see a few clicks from the BWG. And here, that's where we think that sea depth comes in. So we notice at the northern and southern site, that's where we mostly see Cuvier beaked whales. So that those sites, the water depth is deeper. And then the western site, which is this shallower site, is where we see the Gervais whales. So from these click counts, we can input those counts into an equation which can then give us density estimates. So here we are looking at the density estimates for the northern and southern site. We're not including the western site here because we don't have data from 2007. So the top row gives density estimates for all 3 species averaged over our 2 study sites. So the first 2 bars, the blue and red one, are the density estimates in July 07 and 15. And then the next 2, the green and red, are for September 10 and 15. So what we see is what appears to be a general trend of increased beaked whale abundance at these sites. And then at the bottom row, we distinguish between the northern and southern site. And when we do that, we can see that there's a definite increase in beaked whale abundance at the northern site, whereas at the southern site, it's a bit difficult to tell what's going on. And one comment I want to make, so these changes in abundances, they can't be accounted for by reproduction, so it's really movement within the Gulf that's causing these changes. We can apply a similar process to get estimates for sperm whale density. So this first graph gives us the number of clicks per day at the northern and southern site in 07 and 10. And then the graph on the right gives the resulting density estimates. For the light gray bars, that's the northern site, the first three are the density estimates obtained from the 3 buoys in 2007, and then the fourth is for the 1 buoy we had in 2010. And then the dark gray are density estimates for the southern site. Again, the first 3 are from 2007 and the last 2 are from 2010. So what we can observe from these estimates is that sperm whale density appeared to have decreased at the northern site, which is the site that was closest to the spill, and increased at the southern site. And then preliminary sperm whale density estimates using the 2015 data suggest that the sperm whale densities at these sites have not returned back to their pre-spill densities, as we can see from these light blue bars. So in summary, from our acoustic study, we were able to observe 3 types of beaked whales, the Cuvier, the Gervais, and the BWG. In terms of activity and density estimate, abundance estimates, the Cuvier appear to be the most abundant at our sites. Overall, we observed an increase in beaked whale abundance after the spill. And in particular, if we distinguish between the 3 types of beaked whales, and we account for the fact that we have data collected from different months of the year, so there's variability in that data, we can say that there was a definite increase in the Cuvier at the northern site, whereas it looks like the Gervais likely decreased in density at the southern site. And then similarly for the sperm whales, we observed a decrease at the northern site and an increase at the southern site from 2007 to 10. And then our 2015 data seems to suggest that those densities have not increased. Okay, so that leads to the second part of this talk, which is using modeling as a complementary tool to acoustic data. So as I mentioned, the acoustic data we collected can be used to understand immediate responses of sperm whale and beaked whale populations, but they don't tell us anything about the long-term trends. So for instance, we observed that beaked whales in particular don't appear to avoid areas of the Gulf that were impacted by the spill, specifically that northern site. And as people have mentioned earlier today, if they're not avoiding these areas, then they're being exposed to these toxicants, which may end up having health impacts on them, which could affect long-term densities. Right, so our acoustic data can't tell us anything about what long-term trends may be, but instead what we can do is we can use some mathematical models that can give us an idea of what could happen in the future. So here I'm just going to give kind of a big picture idea of how we develop these models and what type of information we can gain from them. So if we want to understand how a disturbance like an oil spill is going to affect a population, first off we need to know things about the population itself, such as its survival rates, fecundity, maturation time, etc. And then we need to know things about the disturbance. So how long was its effect? What was the magnitude of impact it had on the population? So for this talk, I'm going to focus on a model for a sperm whale population, but I just want to note that this model formulation is general enough to be applied to other species. All right, so this figure here is a pictorial representation of what our mathematical model looks like. So basically, we first identify what we think are important biological stages for sperm whales. So in this case, we're using 5 stages. There's 2 immature stages and 3 mature stages, where the 3rd stage is the reproductive stage. We then describe how individuals can move between these stages. So for instance, from one year to the next, they may remain in their current stage, or they could mature to the next stage. And through this description, we can write down a mathematical model that will tell us what the sperm whale density will be through time. And in particular, using information available from the literature regarding sperm whale vital rates, what we found through this model is that the sperm whale population is growing at approximately 1% per year. So that means that the population is increasing, but if it experiences a disturbance such as an oil spill, that could have a significant impact on the population because it's not growing very quickly. All right, so next we need to think about how we incorporate a disturbance into this model. So in our case, we care about the impact the disturbance has on the population. So we're going to describe the disturbance in terms of how it affects my vital rates. So the vital rates could be fecundity or survival. And basically what we have is that when the effects of a disturbance are present, we're going to assume that that causes a reduction in these vital rates. So that's indicated by this red line. And then eventually over time, those effects will go away and the vital rates will return back to their pre-disturbance values, which is given by the green line. So obviously you can see that this is a very simplified view of what a disturbance may do to a population, but it can give us a good estimate, and it also makes it easier because we don't need a lot of information on the environment. In particular, what we need to know are how long does the disturbance affect the population, what is the magnitude of that effect, and if we're interested in multiple disturbances, how often do they occur? So at this point, I have to confess, I'm talking about sperm whales, and we have no idea what those values would be for a sperm whale population, right? But that doesn't, I'm a mathematician, that doesn't stop me, right? So what we can do is we can examine a range of possible values. This can give us just kind of a better idea of what type of patterns we might observe, and we can also, as you'll see, learn some useful information. So as I said, what we're interested in is the population size over time. In particular, if I have just a single disturbance, I might be interested in how long it takes the population to recover to its pre-disturbance size, this is similar to some of the models that you saw earlier relating to dolphin populations. So this is just a pictorial representation of what we mean by recovery time. So each of these blue lines is a population size over time, right? So what we see is that when the disturbance occurs, your population decreases. Then eventually the effect of that disturbance goes away, your population begins to increase, and the recovery time is denoted by these red dots. That's when the population reaches its pre-disturbance population size. So using our mathematical model, we can obtain information like the following. So this looks at the probability that the population will be able to recover within either 50, 100, or 150 years. And it's considering two cases. So either the disturbance causes a reduction in survival or it causes a reduction in fecundity. And so in particular, what we can note here is that sublethal impacts, so disturbances that impact fecundity, have far less of an impact on the population. So in particular, we can see on this right graph here that if fecundity is completely stopped for 10 years, then there's still a chance that the population can recover within a 50-year period. Whereas if I look at the left graph, if my survival is reduced by more than 5% for 10 years, well then it's unlikely that the population will recover in 50 years. And this kind of pattern we're observing is something we would expect for long-lived species like marine mammals. Another thing we can look at is the sensitivity of the recovery time to our input parameters. So basically, sensitivity is if, for instance, I increase the magnitude of impact of a disturbance, how much does that increase my recovery time? And one thing we learned from doing this sensitivity analysis is that the recovery time is always more sensitive to the magnitude of impact than the duration. So this suggests that if there are some types of management strategies that can reduce the impact, that should be where the focus should lie. All right, and so as I mentioned, so recovery time assumes that we only have a single disturbance, and then afterwards the environment is good, right? But in reality, we might expect to see multiple disturbances, as is shown in this graph on the left. So the top is environment, so each of those peaks denotes a disturbance. And the bottom shows the population. So we can see that when a disturbance occurs, the population declines, the effects goes away, the population increases. So in this case, we can't really talk about recovery, but we can talk about whether or not the population will go extinct, or the probability of that. Here's the example in the right graph. So we see the population given by the blue line is surviving, whereas the population given by the red line is going extinct. And we can make similar graphs, again, looking at different ranges of the length of effect and the magnitude of effect, and looking at what the probability of extinction would be for the population. And then interestingly, an interesting result, so if we do sensitivity analysis on the growth rate, which will determine extinction in this case, what we see is that, again, the growth rate appears to be most sensitive to this magnitude of impact. All right. So just in summary, we developed mathematical methods that can help us to better understand how a disturbance may impact a population. Here, as I mentioned, I don't actually have any data for sperm whale populations, but if we obtain data, either for sperm whales or for another species, that data can be implemented in these models to obtain better predictions. And then also, I just want to point out here that even without having data, we can still observe trends in the model output. So for instance, we've been observing that this magnitude of impact of a disturbance seems to be one of the most important factors when looking at the population recovery. And that's it, and here's just a few references that contain this information. All right, thanks.